called your depletion capacitance also. Okay. Depletion capacitance, because it arises due to depletion reason. That's why we call it depletion capacitance also. So what is basically depletion capacitance? You have a PN junction, okay, and you have a depletion layer. So this depletion layer width, okay, is a function of voltage. So whenever you apply voltage, if you apply forward bias, okay, forward bias, okay, depletion layer width decreases. If you apply a reverse bias, okay, your depletion width increases. So if I plot my abrupt PN junction, okay, so this is my abrupt PN junction. You have your X, this is your XN, this is your XP. Huh. Yes.
Depletion
Yes.
layer with the decrease or increase?
Depletion layer width is the width, na?
Yes, sir. In reverse
So
bias, increase or decrease?
reverse bias it increases, na? Because what is your formula? Your formula for reverse bias is what? And the depletion width is what? 2ES upon Q, okay, VBI minus V upon N effective. Okay. Now, if your forward bias, okay, in forward bias, your V equals to VF. So it will decrease compared to VBI. VBI will decrease, and if you reverse bias, then you have V equals to minus VR. So this portion will add here. So will add, your width will increase. Okay. So this is your P side. This is N side. So N side we have plus charge. Okay, here you have minus charge. Okay. So suppose this is the width. Okay, at some potential V. Okay, because with applying potential, this width is varying. Forward bias it is decreasing, reverse bias is increasing. Okay, now suppose this width increases. So this width increases. Now if I increase the voltage, so suppose in reverse bias, okay, I'm applying voltage. Okay, so say I'm adding dV voltage here. dV voltage more compared to this one. Okay, so say this is my, so this is the width at voltage V, okay, and this is width my at voltage V plus dV. Okay. Okay, so that means when width varies, that means your charge also changing. Charge inside the depletion is also changing. Okay, and we know what is capacitance. Capacitance is defined. Okay, C. This is junction capacitance. So I can write D is equals to dQ upon dV. Okay, so whenever your charge varies with voltage, okay, that system gives you capacitive effect. Okay, so here also, because width changing with voltage, okay, either decreasing or increasing, that is a different thing. Okay, but you have a capacitance effect in this system. Okay, so whenever you make equivalent circuit of PN junction, okay, so along with resistance you also mention this capacitor. Okay, along with this diode you also show a capacitor also. Okay, so this capacitance value is very low, but still there that is a significant impact. Okay, so in switching circuit, it reduces the speed how you communicate the signal. Okay, so because of this junction effect, your speed you cannot achieve very high speeds in these diodes. Okay, so now this Cj is given by dq by dv, so I will take this mod. Okay, mod of dq by dv. Okay, now I know what is charge. Charge already we have seen several times. Charge is nothing q nd xn a, and you can also write charge by q na xp a. Okay, So you can use any expression of charge and you can differentiate. Okay, I am using this first one. So if I take this charge, I say dq by dv. Okay, so dq by dv will be q is constant, nd is constant, a is constant. So this will give me what? Dxn upon dv. Okay, now my aim is to calculate this dxn by dv. Okay, so that will give me my capacitance. Okay, now I know what is my xn. So my xn is, we have seen yesterday, xn depends on na plus nd w. Okay, and w is again the function of voltage. Okay, na plus nd, and w is your 2 esq and effective. Okay, w is a function of voltage, so I can write vbi minus v, a general expression. Okay, now I want to differentiate this one, so dxn by dv. Okay, so what will give me? It will give me na. Okay, na plus nd. Okay, these are constant, so I will be keeping like this, 2 es. Okay, q and effective. Okay, now I will differentiate this one with respect to v power, so it will give me what? Half vbi minus v power minus half. Okay, and when I differentiate v, it will give me minus, so this will come with minus sign. But minus we can leave out because the definition of Cj is dq by dv. So minus is not important. So you can a little bit solve further. Dxn upon dw. This will give me what? Now this is an effective. Okay, and here also I can form n effective if I multiply by nd. Okay, so if I multiply by this by nd here, this become
dxn by dv will come, na?
huh?
dxn by dv, na? How
हाँ ये
dw?
dxn by dv था यहाँ पे.
मैंने नीचे लिखा है तो dw लिया है ना?
कहाँ पे? ये वाला, ये एन
नहीं नहीं
इफेक्टिव है.
नहीं नहीं वहाँ नहीं सर, थर्ड
Okay,
स्टेप.
okay, this is dv. Okay, so I am multiplying by this nd, so I will divide by nd. So when multiply by nd, this become my n effective. Okay, so I can write this as a nd. Okay, I can write it like this now. Okay, and now I have this under root. Okay, I have es. Okay, I have 2 here. If I 2 go inside, this become under root 2. I have q. Okay, and I have n effective also, this one n effective, and I have vbi minus v power minus half. Okay, now just a little bit more calculations, then we can get the expression for capacitance. So now I can cancel out this n effective. Okay, if I cancel out n effective, what I'll get? Okay, so I can write directly dq by dv. Okay, dq by dv, okay, is equals to what? Q nd a. If I put the value of dxn by dv here, so what I can write? Okay. So dxn by d effective. Okay, what become? This become under root n effective. So what I'll I will be having under root n n effective es under root e n effective. Okay, and 2q is already there under root. Okay, and 1 by nd also there. So 1 by nd outside, and I have vbi minus v power minus half. Okay, so and minus also there, of course. Okay, so minus also there. So minus also there. So if I take now this nd I can cancel. Okay, so I will be having dq upon dv equals to minus. Okay, this how can I write? I can write this as a es.
Sir, why we take a high here minus sign?
Minus came from here, na?
Sir,
When I
before
differentiate.
you have omitted na one of the minus sign.
और कौन सा और कौन सा माइनस है? एक ही तो माइनस है।
हाँ वही माइनस हमने ओमिट किया था ना।
वो अमिट नहीं किया अभी तक मैंने, अब अमिट करूंगा ना आगे, अभी अमिट नहीं किया, वो सेम साइन ही है। ओके, so this is your ES and effective. Okay, you have 2Q and you can write here. Q is also there here. Okay, so if I bring Q inside, so Q will be here, Q will come here. Okay, and now I have a BBI minus B inside this power half, so I can bring it down. Okay, now can you see it's forming like a W function, W expression. If I multiply by this ES, okay, so this 2 ES VBI, this become 1 by root W. Okay, so what I can write now, so this is minus
Sir, A भी आएगा.
Sir,
A is also there.
Sir, A भी है sir, A.
A you can keep outside. Okay, now what you can write here, okay, you have minus A, okay, and you multiply this here by ES and divide by ES. Okay, so if I multiply by under root inside ES, this become ES square, I can bring ES outside. Okay, and under root what I can write, under root will become Q n effective, okay, 2 ES BBI minus B. Can I write like this? Okay, now this is what, this is W. So I find CJ depression capacitance has become dq upon dV. Okay, I can now remove minus sign, so I have now ESA, and this whole expression is 1 by W. So this become like a parallel plate capacitor, isn't it? So this is the expression for your capacitance. That's why it's giving like a capacitance behavior, where the width is the like conventional capacitor, you have a 2 plates and you have a width. Okay, so here your this distance D between the plates is equal to W, and you have charge separation at this distance. Okay, now if we do a little bit more, okay, we can actually, by measuring this capacitance value in laboratory, we can measure the doping profile. If we can know how much the concentration we have doped in our PN junction. Okay, so for example, if I take now a heavily doped PN junction, okay, so suppose if I take now, okay, so for suppose my PN junction is P plus N type. So PN junction. Okay. So P plus N junction, I know my Na is greater than Nd. Okay. So my N effective. So my N effective will be only equals to Nd. Okay. Now I have Cj. Okay. Cj is nothing. Cj is Es by A W. Okay, where I know what is W. Okay, so now if I take capacitance per unit area, Cj by A, C dash equal to Cj by A. If I take capacitance per unit area, I can write Es by W. Okay, and now this is my Es, and my W is, we know W is what? W is 2 Es VBI minus V and Q. N effective, now N effective will become ND for this particular case. Okay, now if I take this reverse of this Cj square and make it a square, okay, so the Cj is 1 by Cj square will give me what? W square Es square. Okay, and if I put W value, what will get W value? If I put W value, I can get 2 Es, okay, VBI minus V Q ND, okay, and Es square. So Es cancel, so I'll get what? I'll get 2 Es Q ND VBI minus V, this type of relation. Now I can plot this relation. I have 1 upon C dash Z, okay, C dash Z square is equals to 2 ESQND, okay, VBI minus V. Now this equation, okay, this is the line, this is a straight line equation. If I plot 1 by Cj square versus voltage, okay, this become Y and this become minus mx, okay, Y equal to minus mx plus type of equation. So if I want to draw this line on a curve, okay, you can do, and you can, by measuring the slope, you can measure what is the laboratory by measuring this Cj square and plotting this way. You can know what is your concentration in the PN junction, okay, what is the doping concentration. You can also find VBI value by experimentally measuring the capacitance values, okay. So if I plot this one now graph, we plot this graph 1 by C dash Z square, okay, so this is Y and this is a negative slope, so this equation will come like this, okay, okay, and slope of this graph, okay, you can measure in both sides, you can measure in forward bias, reverse bias, okay, capacitance value will be increasing in reverse bias, okay. So now you can plot this slope value, okay, 1 by Cj square will increase, okay, in reverse bias, okay. So now you can plot slope will become what, 2 ESQ ND, and where this 1 by Cj square is 0.
Minus will come, na?
Hmm?
Minus will
come. Okay, of course minus will come. Slope is negative, so minus will come. And 1 by Cj square is 0, then your VBI equals to V. Okay, so this point where it is cutting, that is your VBI. So experimentally, you can measure your VBI value, okay, as well as VBI value, and then you can also measure by measuring the slope, you can measure the doping profile, okay. So by measuring, okay, slope of this line, okay, we can estimate doping concentration.
Excuse me, sir. Sir, Cj was our junction capacitance, then Cj dash is Cj upon
this Cj dash is junction capacitance per unit area. Okay.
per unit area. Okay.
Yeah. Okay. So Cj dash is junction capacitance per unit area. Junction capacitance per unit area. Okay. Now this was your abrupt PN junction. Okay. There's one more type of capacitance, diffusion capacitance also. Okay. So but we are not dealing with that one. Now this was your abrupt PN junction. Okay. Now similarly, I can erase this one. So now I can do it for your linearly graded junction. Okay, this was abrupt junction. Now I'm considering linearly graded junction. Linearly graded. Okay, so in reality, no junction is abrupt PN junction. Okay, so let me draw now linearly graded junction. So what do you mean by linearly graded junction? So now if your charge, okay, if you have a charge density varying linearly with x, okay, this is your x and this is your rho. Earlier it was abrupt, okay, now it is not abrupt, it is linearly varying. As you move away from the center of the depletion layer, the charge density is increasing, okay. So if it is varying, and say this is my w by 2 width, and say this is my minus w by 2, okay, and charge which is given as QAX, okay. So I'm keeping charge densities almost equal, so this become p side, P side we have a minus, okay, and here we have plus, okay. So for this type of charge profile, okay, what will be the profile of electric field, what will be the this E max, and what will be the built-in potential, that we will calculate like we have done for abrupt PN junction. Okay, so it is quite easy. Now once we have done for this abrupt PN junction, now you can do it for now this linearly graded junction. Okay, you know how to calculate electric field. So electric field can be calculated by your Poisson equation, d upon dx equals to rho upon es. Okay, now rho is given already, is q ax upon es. Okay, now if you want to calculate electric field, you can just do it d. Okay, d equals to qa upon es dx. Okay, so e will be what? E will be q a es x square by 2 and plus c. Okay, and this constant can be calculated because we know at boundaries at x is equal to plus minus w by 2 your
Sir,
ex.
integration of
Yes,
dx will come x only, na?
huh?
Why it is square by 2? Integration of dx x will come, na?
Yeah, यहाँ पे x भी था ना, x dx. You have profile qax. Okay, qax. So it will
Okay.
come x square by 2. Now put ex 0 at w by 2. Okay, so this 0. So this will give me qa 2 es. Okay, this will be w by 2 square. Okay, plus c. Okay, and this c value will come minus this one, so I can write my field, okay, electric field value. So I can write my electric field x as qa 2 es. Okay, common, I can take common here, also 2 is common, so it is common, so I can write x square minus w upon 2 ka whole square. Okay, so this is my electric field expression for this kind of junction. Okay, now if I plot, this is like a parabola. Okay, I know at w by 2 at the boundary it is 0 and somewhere here it is maximum. Okay, so at w by 2 minus w by 2, this is electric field, okay, as a function of x, and here it will be maximum. Okay, at maximum you can put x is equal to 0. So when you put x is equal to 0, this will give you qa 2 es into, okay, omega square upon 4. Okay, so this become total 8. Okay, so E max value for this type of junction, I can write E max value is qa omega square and 8 es. Okay, you should also remember the dependence also. Okay, how E max is depending on w, how w is depending on built-in potential. That type of question they ask in exam. Okay, so we'll see now. So this is your E max qa upon w
Where
square.
it comes means
Huh?
how you put that
Huh?
is in that graph how q a upon 2s into omega square 4 will come at that point.
You put x is equal to 0 here, na? This is x is equal to 0, na?
Okay, okay.
Okay,
Sorry.
so you got E max. Okay, so this is your expression for E max. Now also you can find built-in potential VBI also. Okay, so VBI, how can you find VBI? Is simple. Now you know the electric field. Okay, you can differentiate minus omega by 2 to omega by 2 your electric field E dx. Okay, or whatever you're writing E like this, or whatever way you're writing ex. Okay, dx, just put the this value here, integrate, and you get the expression for VBI. Okay, so VBI will be now your minus, okay, I have this QA 2ES, okay, integrate minus omega by 2 to omega by 2 x square minus omega by 2 whole square dx. Okay. So you can write your VBI minus QA 2ES, okay. Now differentiate, integrate this one, okay. So when we integrate this one, what you get? I get x cube by 3, x cube by 3, and if I integrate this one, I get omega by 2 square x, okay. The limit is omega by 2 to minus omega by 2 or w by 2. So now VBI क्या हो जाएगा? I can write VBI is equals to minus QA upon 2ES. Okay. Here you put the value here. So if I put the values here, okay, I'm erasing this one. So this put W here. So this become W cube and become 8 and 3. This become 24. Okay. Minus you put minus W by 2 here. So what will become? Okay. So you already put this W. So now put here W
So we
here.
can put 0 to w by 2 and multiply by 2.
If you check it, this function is even or odd. I don't know. Okay. So let me solve this one. Okay. Put omega.
3
This
by
become
24.
omega q. Huh? यहाँ पे
check
2 है ना 824. I put omega by 2 here, so omega q, omega 2 and 4. This will become omega 8. Okay. Now I put minus again inside. Again I put minus omega 2 here. This will become minus omega q upon 24. Okay. And this now again
minus w cube by 8.
Okay. Now this is minus. So what will get here? I'll get
Minus w cube by 8.
minus become plus w cube by 8. Okay. So if you solve this one, minus qa 2es, okay, you have this minus plus, so you have a omega q upon 12, okay, 25 2 plus. Similarly you have this omega q 8 here and minus here, so you can write minus omega q 4 here. Okay. Now are you getting what I'm doing? Okay. This omega q will just become add, so become 12. This become adding, become 2 omega q by 8. This become omega q upon 4. Okay. So now you have minus qa 2es. Okay. This will give you what? If you take 12 common, so this will give you omega cube. Okay. And 3 omega cube. So if you simplify this one, we should use 12. Okay. So VBI is equals to minus QA, okay, 2ES into this is minus 2 omega cube upon 12. Okay. So minus become plus, and you 2 cancel. So you will get the expression VBI is equals to QA omega cube upon 12 ES. Okay, so this is the built-in potential for your linearly gated junction. Okay, this is for linearly gated junction. For abrupt P junction, we have square. Here we have cube. Okay, now we can see this is in different way. Okay, so I know the width again depends on voltage.
Sir, It's linearly graded means concentration varies linearly, hence the name. Is it so?
Yes. Since concentration varies linearly, that hence the name linearly graded junction. Okay. And now you can write omega cube. Okay. Omega cube as 12 ES. Okay. Upon QA. And instead of writing VBI, now you can write V, general expression, and this W, and this you can put power 1 by 3. Okay. So this is the relation we are interested. Okay, because the question asked from this relation. Okay, so we can write that for a linearly graded junction, okay, for a linearly graded junction, my width is proportional to VBI minus V power 1 by 3. Okay, this is for linearly graded junction. Okay, and for abrupt we already know, for abrupt W is proportional to BBI minus B power half. Okay. So this is the relation you have to remember. Abrupt junction. Now, same line, if you continue, we can also calculate the junction capacitance also. Okay.
Sir,
Uh,
forward bias, reverse bias are as previous only, na? That the
uh,
VBI
the-
minus
yes, yes,
V
yes, yes, yes,
V
yes.
for
Yeah,
one.
V is same. Okay. If V is forward bias, you can put here with positive sign. If reverse bias, you put it with reverse sign. Okay. So if you want, you can put minus plus also here. For reverse bias, you can put plus VR here. Okay. Now let us calculate junction capacitance also. Okay, that also is easy. So shall I read this one? Okay. So just remember this formula. Okay, we will be requiring this formula
Yes, sir.
of W. So now junction capacitance. Okay, for linear degraded junction capacitance. Now junction capacitance, in order to calculate junction capacitance, we first should know what is the charge value. Okay, so earlier we were knowing the charge value. Here we need to calculate charge values. Okay, so here you have been given rho. Okay, rho is QAX. Okay, so you need to find the charge. What is the charge in this region? You given charge density, so you can calculate charge. Okay, so what is the charge between 0 to in this region? Okay, same will be this region with negative sign. Okay, so if I want to find charge, so charge is simply what? Rho dx. Rho dx. Okay, limit from 0 to W by 2. Okay, so 0 to W by 2 Q A X dx. Okay, so this will give me what? This will give me Q A half. Okay, x square by 2. Okay, so that will be, so let it do it. X square limit is x square by 2 0 to W by 2. Okay, so the Q value becomes, okay, Q A by 2. Okay, x square is W by 4. So this become 1 up by 8. Okay, Q A W square. So QA W square by 8. Now you know what is W value in this particular case. So you can put a W value here. So you get 1 by 8 QA. Okay. What is W value? What is W value? 12
12
ES
by
VBI.
2A VBI minus VI to the power 1
Okay,
By
here
QA.
QA.
upon QA.
QA. So this power become what? 2 by 3. So earlier it was 1 by 3 V. So this square is become 2 by 3. Okay. So this is your expression for charge. So you have charge now. Charge is equals to Q. Okay. QA by 8. Okay. 12 ES VBI minus V upon QA power 2 by 3. Okay. Now just differentiate this equation. C. Okay. dq upon dv, keeping the positive value. Okay. So if you differentiate this one, okay, I'm just writing the final expression. Okay, because I need only final expression. So I can get the final expression by differentiating this one. Of course, this will be your Cj by A. A will be there or not. This time A will be there or not. Okay, so A is not there here because we have not calculated A. Okay, we have already charge densities given. So I can write, when I solve this one, I'm writing only final expression QA. Okay, ES square 12 VBI minus V. Okay, and whole power is your 1 by 3. This type of expression I will get. Okay, 2 by 3. Okay, so dq by 2 by 3 minus 1 by 3. I'll get minus 1 by 3. Just check it. What is coming? Minus 1 by 3 or plus 1 by 3. Okay, so if I want Cj, so Cj this time becomes VBI minus V power minus 1 by 3. Okay, this relation I want. This is for linearly graded. Linearly graded. Okay, and Cj was VBI minus V. Okay, just now we have seen before, that is for abrupt PN junction. Abrupt PN junction. So this expression, this dependence on N, you should remember. Okay, so this is a linearly graded junction. Okay, similarly we can do x square, x cube, x4, xn. Okay, we can do a generalize, and for generalize this n power we can find this expression, but that much is not necessary for your course. Okay, so I'm doing only up to linearly graded. Okay, so this is your PN junction thing is finished. Okay, now
Side,
yes.
just side, want to copy.
Mhm. Just once check these expressions whether it's correct or not, but we just want dependence. I want this dependence only. This calculation, this constant is not important for me, so you just check it. Okay, now we have finished our PN junction. Okay, now we are moving towards diode. So before moving diode, we need to understand IV characteristics of PN junction. So after explaining IV characteristics of IV junction, this PN junction, we will start our diode. Okay. So let me discuss IV characteristics of PN junction. So now onwards there will be no calculations. Okay, after this. So now IV characteristics. Okay, of
Sir, expression
PN.
is correct. We got same. Expression is correct. Same dependence in we get.
No, one is 1 by 3, one is 1 by 2. Na?
Yes, sir.
One is
Whatever
1 by
you one
minus 1
by
by 3. One is minus 1 by 3, one is minus half.
yes.
So IV characteristics of PN junction. Okay. Now, whenever you apply a forward bias to PN junction, okay. So you have this PN junction. You are measuring I, you are applying voltage. Okay. So when you are applying to a forward bias to PN junction, okay. So what will happen? You will get current. Okay. And you know this current is exponentially depends on voltage. Okay. Similarly, if you plot a curve on reverse bias, if you apply a reverse bias on PN junction, okay.
सॉरी
So हाँ
सॉरी सर, प्रीवियस जो हमने किया है
हाँ
उसमें जब हम ये सीजे निकालते हैं तब साइलन एस अपॉन डब्ल्यू आ रहा है, मतलब दिस इज कमिंग लाइक सीजे पर यूनिट एरिया, लाइक सीजे डैश आ रहा है ना ये।
here it is CJ. Here area is not there na. Here we have already given charge density. So we have when calculated charge, we just integrate that one. So area was not there na. So here you know no need of you just calculate capacitance CJ. That was per unit area capacitance. There also you can put A there na. No issue na. Dependence same. If you put CJ dash, you put CJ dash is what? CJ by A. So whatever expression you get for CJ, just multiply by with A. That will be CJ dash. That A is also constant.
सर मतलब यहाँ पे जो ये एक्सप्रेशन हमने कंपेयर किया ना,
हाँ
जैसे हमने, तो अगर ये कंपेयर करूं तो यहाँ पे जो सीजे है वो सीजे डैश तरह पे आ रहा है ना।
वही मैं कह रहा हूँ ना. CJ is what? CJ is A CJ dash ना.
यस सर।
So you just multiply this with A. A is also constant na. I just want dependence on I have compared CJ. Okay. Dependence on voltage. So dependence on voltage is same for CJ and CJ dash same.
ओके सर, ओके।
Okay. So A is constant. Okay.
Means for linearly graded, we get CJ is proportional to na VBI minus V raised to minus 1 by 2.
तो CJ I written as the same thing na. A is constant. We both the same thing. Okay.
डिपेंडेंस इज सेम।
Dependence same. So now you are writing this PN junction, okay, and we know, okay, here you got exponentially increasing current, and reverse bias only saturation current flows, okay. So in reverse bias only saturation current flows, and the current is very almost linear, very low current, okay. And at particular point breakdowns occurs. This is called breakdown voltage. So this is your IV characteristics for a this your PN junction. Okay. Now for this IV characteristics, okay, there is a diode equation. Okay, it's also called Shockley equations. So the Shockley equations is given by, okay, or you can say diode equation. Adding diode equation. Diode equation is given by IS, okay, exponentially, okay, QV upon eta KT minus 1, okay. This is your diode equation. So this equation, okay, if you do for now here, what IS is what? IS is a reverse saturation current. IS is reverse saturation current. Okay. B is applied voltage. Okay. For forward bias, this will be positive. Reverse bias, this will be negative value. Okay. And eta you know, eta is what? Eta is ideality factor. Eta is ideality factor. Okay. Eta values are 1 for germanium PN junction. It is 2 for silicon. Okay. And if there's nothing is given, you assume ideal. So ideal case you can take also 1. Okay. In question, if nothing is given, if it's a germanium, okay, then you can put 1. If it's silicon, you can use 2. And if you say ideal, and if say silicon ideal, then also you put 1. If I most of the case you put eta equals to 1. Okay. Especially they are mentioning that germanium you take 1, For silicon you take N2, then you have to take N1 or 2. Okay, so this is your diode equation. Let me write this diode equation in another form. So I can write this diode equation like this also, exponential. Okay, I can QV. Okay, I can write like this VT minus 1 also, where VT I know what is thermal voltage. Okay, if I want to write VT, so VT is what? KT by Q, thermal voltage. Isn't it? So I'm bringing Q down. So this become KT by Q. Okay, so this become VT.
So you have taken eta 1 here.
Eta you
Manu?
can put eta also here. You can if you want you can put eta also here. Okay. This is the diode equation. Okay, and this is also called Shockley equation. Shockley equation.
So thermal voltage means it shows how voltage varies with temperature or something.
Yeah, thermal equivalent of voltage. Okay, you put different temperatures here, you get different voltage here. Okay, so thermal equivalent to voltage. Like if you put T equal to 300, you got VT equals to 0.026 electron volt. और निकाला था ना हमने cut off VT. Okay, so KT by Q at temperature. So this varies with temperature. KT means KT is energy. Energy by charge is voltage. Okay, you have energy, you multiply by Planck constant. Okay, so you know what is K. K is Planck constant here. K value is 1.38 to 10 raised to power minus 23 joule per Kelvin. Okay,
Sir, here V is our applied voltage, na?
V is
That
V is
we
applied. Yes, V
applied.
is applied voltage. V is
Okay.
applied
And
voltage.
VT is our
Thermal
thermal
voltage.
voltage.
Okay, so V is applied voltage. Okay. Okay, so now let me discuss this IV characteristics with this with the help of this equation. Okay, so I have this I equals to IS exponential. Okay, V upon eta VT minus 1. Okay, now if I apply forward bias for forward bias okay, for forward bias, this VT is in milli electron volt. We already know, isn't it? Room temperature, VT is milli electron volt. If I take T is equal to 300 Kelvin, my VT is what? My VT is minus 0.26 electron volt, or 26 milli, 26 millivolt. Okay. Now applied voltage generally is in volts. Okay, even you say 0.1 volt, 0.2 volt, 0.3 volt, 0.5 volts. Okay, so cutoff voltage for silicon is 0.7 volt. So you need to apply at least this should be at least greater than 0.7 volt for the silicon, 0.3 volt for germanium diode. So this 0.7, 0.8, 1, suppose this is 1 volt and this is in milli electron volt. So this V is quite greater than VT when we measure the current. Okay, so V is greater than VT. Okay, whenever we measure IV characteristics in our laboratory, we apply voltage. Okay, 1 volt, 2 volt, 3 volts, because this was voltage minimum voltage we require, na? Okay, cutoff voltage itself is 0.7 volt for silicon, so you have to apply more than 0.7 volt to get any current in forward bias. So this value in forward bias becomes greater than T. Okay, so that means this expression we can neglect one. Okay, so forward bias. Okay, for forward bias I can express, okay, I can write my I equals to IS almost equal to IS exponential V upon eta VT. Okay, And similarly, for reverse bias, okay, what I can do, I can write, okay, my applied voltage is minus VR. Okay, here you can write V forward. Okay, V equals to V forward. For forward bias, you can write V equals to V forward. So this is my equation for current. And for minus, okay, so in the case of minus, what I can write, IS exponential minus VR eta VT, okay, minus 1. Now again here VR is reverse bias, we apply very large voltages, okay, compared to bigger than your forward bias. So VR is greater than VT. So what I'll get from this expression, this become minus infinite, okay, this expression become minus infinite, so this expression becomes 0. Okay, so what I can get, I get I equals to minus
IS.
minus IS. Okay, so only reverse bias, reverse saturation current flows until breakdown to until breakdown occurs. Okay, so before the breakdown, you have only minimum current flows. So that's why before that I have just drawn the IV characteristics. Okay, let me draw it again. So if I draw now IV characteristics, so this IV characteristics, okay, this is like this. You have I here, you have voltage here, and you are here, you're getting almost constant current. Okay, this current is your IS, reverse saturation current, and then breakdown happens some particular voltage. Okay, and this variation, okay, this is cutoff voltage, this is cutoff voltage, and almost equal to your BBI, because if you want to make conduction to take place from junction, you need to apply minimum voltage up to VBI. Okay, so this VBI is nothing, this is a cutoff voltage, this is VBI, cutoff voltage, you can say VBI, or sometimes we write book, they write by V gamma. Okay, so this is 0.6, 0.7 for silicon. Okay, so this is 0. This value is 0.7 volt for silicon. Okay, for germanium, okay, if I put germanium, this value is 0.3 volts. So you can show this value on a scale, 0.3, 0.7 for silicon. Okay, now here you have current milliampere, I is in milliampere. Okay, you're applying here V in volts or some volts. Here also you're applying volts, but this scale here current is what, in microampere. This current is what, reverse current, that is in microampere. Okay, so they are not in same scale. Here you can apply up to 1 volt, 2 volt, 3 volt, 4 volt. Here you can go 5 volts, 6 volt, 10 volts. Okay, so this is, the scale is not same. I'm drawing on same scale, but the scale is not same. Okay, this is called your compensated scale. Compensated scale. Okay.
Sir,
Huh.
please explain difference between breakdown and cutoff voltage. What is
ब्रेकडाउन पे तो जब आपका डायोड फेल हो जाएगा, कट ऑफ वोल्टेज इज द वोल्टेज यू रिक्वायर टू गेट द करंट टू फ्लो इन अ सर्किट in forward bias. Okay, the cutoff voltage is your built-in potential. When you apply forward bias, you won't get any current in the beginning until you don't apply VBI. Okay, so once you apply VBI, okay, greater than VBI V, then current will start flowing, and then it will vary like exponential current. Okay, breakdown voltage is different. Breakdown voltage is occurs in reverse bias. Okay, when you keep on applying voltage, a particular voltage, diode get fail and you get large currents. Okay, so breakdown we will discuss tomorrow. So I'm just discussing today IV characteristics. Now how temperature affects this IV characteristics, okay, that we will discuss tomorrow. So today we cannot finish it. Okay,
Sir, what is cutoff voltage, sir?
cutoff voltage is your built minimum voltage required to diode to conduct. minimum voltage require
But
diode to
why
conduct.
needs means some fixed amount of voltage only?
Because VBI is fixed now for every diode. I told you what is diode. In your I shown you this energy curve. Okay, here you have this QVBI. Okay, until you don't apply voltage greater than this VBI. Okay, if you apply forward bias, so slowly this barrier decreases. Na? So if you want to make two electron to flow here, to current to flow, current to conduct, okay, you need to apply this voltage. This is a barrier voltage. In PN junction, you have barrier voltage. This barrier voltage is called your cutoff voltage. Okay, are you getting now?
Okay.
Until you don't apply the barrier voltage, you cannot make diode to conduct. Okay, and this is different for different type of
Voltage is barrier
material.
voltage.
Yes, you can write cutoff voltage is a barrier potential. Okay, approximately equals to barrier potential. Cutoff voltage is like your barrier potential. So I'm stopping here. Any question? Any question is there? Okay, and thank you.
Thank you, sir.
Thank you, sir. Good night, sir.
Thank you, sir.